Good morning, everybody. My name is Tasmin Öpöz. I will be chairing this morning sessions today. We have today one keynote speaker, Professor Dennis Wald from Harriet University. Martin is going to introduce him.
So hello. I invited Dennis to give this talk because he has studied this area in some detail. However, what I know Dennis more for is lasers and laser physics. So Dennis did his PhD way back in the 60s at Manchester.
No, United States, Case Western Reserve.
For his degree, and he went off to the States to do his PhD in laser physics. He came back to the UK and he worked at the Services Electronics Research Laboratory. I was just pointing out to Dennis that if you go onto the website for Cafe News Newsreels, you can see how these guys operated in 1967. Dennis hasn't seen this, but if you do a search on Cafe Newsreels for lasers, you could possibly pick up a laser video from 1967. Following that, Dennis then became an academic and worked at Heriot-Watt University, developing laser sources, and as a result of that work he has co-founded three laser companies, all very successful. One of them established now for how many years? Laser applications?
25, oh, no, that's 35.
So he's done very well. He was also pro VC at Heriot-Watt. And now in retirement he has found himself working on a national strategy for laser processing in the UK in a role related to the EPSRC Centre for Innovative Manufacturing in laser-based production processes. And that's principally how I know Dennis, because with my contacts in Aden, we've been working together on this. And it's an important activity to try and increase the use of lasers in the UK. So, what's that all got to do with fracking and why here? That's because Dennis actually lives on the Wirral, and as you're aware there's a lot of debate and activity related to fracking. And Dennis has spent a lot of time researching fracking, and we have spent time together with Dennis telling me, and I think that he's got very sort of important findings of this research to share with us. And so I hope you find this very interesting. I'm sure it will be. Dennis, over to you.
Okay, thank you, Martin. Thanks very much for your kind introduction, and good morning, everybody. Thanks for the invitation. I actually think for me it would be a lot more fun to talk about lasers, but our topic today is oil and gas, and in particular the topic relating to what's now called unconventional gas extraction. Gas extraction didn't used to be called unconventional. It used to be very conventional. Unconventional, I'll explain how that term has arisen. My interest in the subject came only because I heard so much about it from the point of view of great controversy, people on either side of the argument. But what I didn't find was a lot of information on which one could base a judgment. There are a lot of assertions, but not much evidence. So hence I spent some time trying to understand what are the key processes, and that's what I'll try to talk to you about today. So my aim today isn't particularly to convince you of anything. I'd like to provide, as far as I can, what basic science we need to understand in order to see why these processes have developed the way they've developed. They've developed basically because it became clear around the turn of the century that we're running out of, quote, conventional ways of getting oil and gas out of the ground. Conventional means you just find where you think there's some oil, you do your seismics, find out where you think there's some oil or gas, and you sink a vertical well, and if you did it right, you can suck oil or gas out for quite a long time. Those places became harder and harder to find, and so people began to look at alternative places where oil and gas is stored under the ground, but which have been ignored simply because of certain physical properties of the of the reservoir where the oil and gas is quote, stored. So my approach is to try, as I said, to try to see just some small bits of basic physical properties of rock formations, which have certain consequences, and then to look at the technologies which have been developed to try to get around the difficulties which the physical properties have caused, if you like. So I'll start with a bit of science. Well, I've got it here, actually. Yes. A little bit of history, so we get some context. Some bit of science to do with gases, but particularly to do with physical properties of rocks. And then the technological solutions which have been developed to try to... I saw you make a red light, but I didn't see what you did, Martin. How do you...
It's the right at the tip. There you go.
Okay, thanks. I've got to get the finger in the right place. Okay, so yeah, I'll be looking at the technological solutions to try to get around the extraction problems which the science produces. Not the science produces, it's the properties of the rock which produces. So what processes am I going to are in this category of unconventional processes? This is not very successful, so I'm going to... I don't have it with me. Having no pointer is a bit of a problem. I think the battery must be going. Okay. So the processes, or these are some of the processes which have been given this category of unconventional. I don't have time to cover all of them, so I'm going to cover the one which has caused the most controversy, namely this one here to do with fracking. The others I'll refer to some degree to give you some background, but there's really no time to talk about them in detail. In fact, there's not much time to talk about any of these things in great detail. I'm going to talk about fracking. These are some of the issues which have arisen. I'll basically talk about the technology of fracking, and then some of the consequences and some of the asserted risks. Oh dear, I'm not going to be able to do this very well. I mentioned the fact that I could not find a lot of published evidence when I started looking 3 or 4 years ago. And you can see how the evolution of the published literature has really come on quite a lot in the last few years. In fact, 80% of the papers that have ever been published on the subject of fracking have been published in the last 3 or 4 years, which is really very interesting given that the conclusions which our government has come to with regard to whether fracking is a safe and sensible thing to do or not is a report published by the Royal Society and the Royal Academy of Engineering, which was written in 2011, and as you can see, it's long before much of the evidence was generated. So I'm not saying they're wrong. All I'm saying is that it would be helpful if one adopted the so-called precautionary principle of policy making. One probably would want to make a little bit more cautious evaluation of it and to think in terms of trying to get more evidence than we currently have, and certainly more evidence than was available in 2012. Okay, so where did we start with all this? Well, the first time people seriously began to get gas out of the ground, it was by an indirect process using coal as the intermediary. So mining coal and burning the coal to produce gas. This actually started, or the first evidence of this we have is at the end of the 18th century when a man in Cornwall discovered if he burnt coal and piped the gas and into a sort of rudimentary kind of mantle, he could light his house. And within a decade or so, it became almost the norm for cotton mills in Lancashire and Yorkshire to use gas derived from burning coal in their own local plant to light their facility. And by 1812, I think it was, we had the first commercial source of so-called coal gas, gas derived from coal. So how was it done? Well, this is a schematic of a basic process which continued in the UK until, 1981, I think the last one closed. Basic idea, you take coal, put it in an airtight container, arrange to add oxygen or air and steam, set a fire to it, the gases are produced, and the gases produced particularly are hydrogen, carbon monoxide, and methane, this combination of gases, but unfortunately, in addition, one gets lots of CO2 and nitrogen if you're using air instead of oxygen. And a lot of things you'd prefer not to have, although it turns out they can be quite useful. Heavy hydrocarbons, they're quite useful if you can control them. So you need some kind of filtering processes to take out the heavy hydrocarbons, the coal tar and so on, and to remove the sulfur compounds. And at the end of this, you wind up with coal gas, it's a flammable fuel, it's a mixture of gases, typically it's called syngas. With these gases, plus these heavier hydrocarbons, and for 150 years in the UK, this has been used for domestic lighting, for cooking and heating. I should mention that the process of underground coal gasification is essentially the same process, except instead of having this in a relatively controlled on-surface facility, the idea is that you burn the coal underground and try to control the combustion and the products and what happens to all these nasty things a mile underground. So that's the process of coal gasification, underground coal gasification. The main thing that we're going to be talking about today mostly is methane, which is the main component of natural gas. Natural gas is formed from layers of buried plants and gases and animal remains, which are subject over hundreds of millions of years to intense pressures and high temperatures. And so this is the origin, if you like, of all oil and gas. So it's essentially the energy of the sun driving or innovating biological matter, and then having the energy stored as this energy stored later as chemical bonds in natural gas existing deep underground. This is a non-renewable fossil fuel, a non-renewable source, and its use is widespread. It's very convenient. It's used for electricity generation, domestic heating, cooking, and driving vehicles, and also increasingly as a feedstock for the chemical industry. I'll leave out the chemistry. Let's look at some history for the UK. The UK took its first shipment of natural gas from Algeria in 1964, and then within a year or so, natural gas deposits were discovered in the North Sea. And that triggered a 10-year program in the UK to convert from using coal gas, which had existed in many, many plants all over the country, to natural gas, which would be some kind of national resource. The industry was privatized in 1986, and then 20 years later, it was in fact not all gone, but we had gone from being an exporter of natural gas to becoming a net importer of natural gas in 2006. So I mentioned this use of word conventional as regards to fossil fuel extraction. The one which has been going for the longest time is extracting coal from coal beds, from coal mines, coal seams. A little less, a little more recent is the extraction using vertical wells of oil and gas from reservoirs where oil and gas is collected over hundreds of millions of years, typically in limestone or sandstone. I mentioned that when times got hard, in the sense that these resources were beginning to run out, people began to look for alternatives. And one of the main alternatives that's been explored for the last 20 years in terms of development, and really only in the last decade in terms of production, is extracting gas and oil from shale rock using a process called hydraulic fracturing. As I'll try to show, the process of hydraulic fracturing or fracking, which has become the name for the whole process of extracting gas or oil from shale rock, in actual fact is only one part of a much more complicated process. So the word fracking has become used to describe the whole process, where in actual fact it refers only to some small part of it, an important part, but a small part of the overall process. Another type of reservoir where in recent times this word unconventional has been ascribed is to the fact that in many coal beds methane is a very prevalent component, lots and lots of methane. I don't have time to talk about coal bed methane and what processes you have to use to extract it, except that I'll mention that often fracking these days are also used. And then the final one, trying to take syngas, the same combination of gases I mentioned earlier, emanating from coal by burning the coal underground. Okay, so this is a little bit of physical properties. The main physical property we need to take note of is the property of the permeability of a rock formation. First of all, let's look at porosity. Porosity, a measure of how much open space exists between the grains of the material in a rock formation. And here I show three three important types of rock: limestone, sandstone, and shale. And you can see that there's a lot more space between the grains in limestone than in sandstone, and more than in shale. And I should mention, because scale here is, the magnitudes are important here, the scale on this diagram for shale is 100 times smaller than the scale for limestone. So the difference between limestone and shale in terms of its porosity is much bigger than the sketches actually show. So the key thing with regard to this is permeability, and permeability relates to two factors: not only the porosity of the rock, not only the space between the grains, but also, since we're here talking about it's a measure of the rate of flow that you can achieve of a fluid through a particular material, clearly relates to properties not only of the rock but also of the fluid. So the rock porosity is key, as also the viscosity of the fluid. The fluids we're talking about here are natural gas, or in the case of some shale formations, oil, and various combinations of alkanes leading all the way from the smallest alkane, namely methane, all the way up to oil. Here's a picture of what the rock looks like, shale and sandstone, and you can see the sandstone looks a lot more grainy than this rather solid-looking shale. I should mention also that shale is quite brittle and is subject to being fractured. In fact, this is the basic process which allows the extraction of shale gas from shale to be achieved, is the fact that shale fractures. The fracking process doesn't actually produce much fracturing. What it actually does is to refracture rock which has been fractured because of the intense pressures locally, has been already fractured many millions of years ago. So the fracturing process doesn't actually fracture very much rock, it refractures. That's the general interpretation. Okay, a small equation just as to hammer this home. We're interested in the fluid flow, so let's imagine we were looking at the flow through this sandstone of, say, of gas. The flow rate is dependent clearly on the pressure difference that's generated. It's also dependent on the area. It will increase if the permeability is high, and it will decrease if the viscosity is low. So obviously the flow rate for natural gas will be higher than the flow rate for oil. And some numbers. These are the key things, probably the most important set of numbers of the talk. The relative values of the permeability of shale and the permeability of sandstone or limestone, you can see there's a difference at its extreme of 1,000 million. So 10 to the 9 is the ratio. So what that says is that the rate of flow of gas through shale is extremely small compared to the rate of flow through sandstone. And at the pressures which exist at a mile underground, to give you some idea, the flow rate of gas in shale is such that under those pressures, it would take of the order of 1 million years for the gas to flow 1 centimeter. So that makes a real problem, given that in conventional reservoirs, such as sandstone or limestone, the flow is much more rapid. And the sandstone itself becomes the reservoir. Okay, so let's look at one final time at the conventional approach. Here's an invented formation consisting of, this is probably the source, in this case, of the oil and gas. And over a few 100 million years, the gas under pressure, because the pressure gradient is upwards, drives the oil or gas very slowly out into the reservoir and then much more rapidly further upwards until it hits a cap, and this cap is where you come to a region, again probably shale, where the permeability is extremely low, so it gathers here. So the process of extraction is you do your seismic analysis, and if you think you found a place where there's gas, you sink a well, and if you got it right, you can take the natural gas or the oil, whatever is the fuel there, for decades. You don't have to drill a new well. Generally speaking, you can do it here, and you go another 10 miles and do it again in another case. So most oil and gas that's ever been extracted over all time has been extracted from reservoirs of this general type, from rock, which is highly permeable, and that's the key to this. And generally speaking, relatively speaking, I don't say it's easy, but relatively it's easy to extract. If we now look at, this is a more complicated, overcomplicated picture, but I don't have any other, I'm afraid. So let me cross out, first of all, over here on the left, this conventional gas. And this just illustrates some of the features of this unconventional processes of taking shale gas, and here's the shale formation, taking methane out of the coal bed, and taking so-called tight gas. Tight gas simply refers to the fact that the reservoir has a permeability which is substantially higher than it would be for conventional sandstone or limestone with other materials in it. And as a consequence, you have to do something, if you want to get a good flow rate, the gas is considered to be, inverted commas, tight. So in order to do something about it, you have to do, basically you have to use fracking, is the standard process to take gas out of tight gas. But it's still very much more permeable than the shale itself. So unconventional sources of gas, tight gas, coal bed methane, shale gas, and underground coal gasification, and I'm going to be talking only about shale gas, really. As I said, less favorable geology, more complicated extraction technologies. So this shows this same thing schematically. Conventional at the top of the pyramid, it's the low-hanging fruit, relatively easy to acquire, and it gets more difficult as we go down. It's interesting to note that in the UK, there are licenses granted pretty well over the whole of the Wirral for, at least for these two processes, and also in the D for this process. If you look at the map of where licenses are granted, pretty well the whole of the UK, from the west coast, from around this region to 50 miles north and 100 miles south, 100 miles north and 50 miles south, pretty well all the way across the country. This is the so-called Bowland Shale formation, and there are dozens of companies that have been given licenses to explore, not to extract at this point. Okay, so the rest of the talk is mostly going to be about fracking, but I'm not going to call it fracking because we need to understand that this is I need to talk about it in terms of its full title, and I can't get the red light to turn on anymore. The battery is gone. High volume hydraulic fracturing in long laterals. The high volume is very important, and the long laterals are very important. I mentioned that fracking has been done in the past, I think as early as the 40s, but this was fracking in vertical wells and with relatively modest volumes of fluid, of 1,000 gallons or two, whereas modern fracking uses up to 10 million gallons of fluid. And it uses not vertical wells, but horizontal wells. It's going to be difficult. I'm going to try and use this one. Okay. So as I mentioned, fracking is only one part of the gas extraction process, although now these days it's used to describe the whole process. So I'm going to first of all talk about the technology of fracking, and then some of the consequences, some of the outcomes, and in particular, I'll talk about these last two, leaky wells and climate change, some recent data on this. So a little history. The key things I want to mention here are 4 factors or 4 technologies which have been developed since the early 90s, which are illustrated here. The first one is the use of well, I've got them on the next slide, so I'll come to them in a minute. This goes back to the early 1900s when people did vertical well fracking, as I just mentioned. And much of the early work was done in Texas, and particularly in the so-called Barnett shale formation. The development of these 4 technologies indicated by the red lines, horizontal wells, slick water, multi-stage fracking in horizontal wells, and the use of multi-well pads, I might as well get to it immediately, is on this slide. So directional drilling means we drill, I'll show you this in a cartoon in a few minutes, but these are the 4 processes which are key to unconventional gas extraction from shale. Okay, so where's the shale located? Well, the shale's located everywhere throughout the shale seam. So this is a shale seam, and it's everywhere. And remember, the permeability is extremely small. So if you have a process which locally can release gas, such as a fracturing process, what that tells you is that you have to do the fracturing process everywhere throughout the shale seam in order to take all the gas that you'd like from the seam. So because of the high permeability of the order of up to 10 to the minus 9 darcies, in fact, the gas is trapped in tiny micro-nano pores, which generally speaking are not connected to each other. So you have to form some other kind of connection. So this is problem number 1, how to release the gas. So a technical solution for gas release is going to be illustrated in this cartoon. So let's look. Here's a section through the earth. Here's the surface, and here's a slice of the rock, of the shale rock. And if I sink a vertical well into here, and I try to take gas out, well, I'll take a small amount, but not very much because of the permeability problem. But then if I fracture it, I can take gas out from a few more areas. And my drawing isn't brilliant, but you can get the idea of the kind of fracturing which occurs. But turns out that this is sort of first generation fracturing. Second generation hydraulic fracturing is rather more focused in terms of what's done. And so that's done by subjecting the subterranean structure to immense hydraulic pressures. So problem is, however, that the fracture zone, the zone around that you can actually achieve fracturing, is a few tens to extreme hundreds of meters. So it's not very large. So problem number 2 is how to access more shale. And the answer is that's the problem, and you have to do it at low cost. So this is where horizontal drilling has come in. So here's my vertical well, but now I'm going to do something more sophisticated and drive the well horizontally through the shale. Of course, this is only a cartoon. This right angle is unachievable. So what actually happens is at some 500-600 feet above the shale where you want to turn, you begin a longer, a gentler transition to the horizontal. This is, of course, an idealized shale formation. Not all shale formations are horizontal. They go all over the place. And one of the, I think, incredibly impressive features of the technology is the extent to which directional drilling has been developed over the last 20 years. There's now several different technologies for this. And basically, you can make all kinds of shapes. And you can, in fact, you can't exactly turn a right angle, but it's much closer to a right angle than it used to be. You can draw spirals, and the other feature which is very important is that you can know very, very accurately where your drill head is. What I'll talk about now is the fracturing process and the fact that we'll do it in zones. Okay, so how do we do this? Well, sorry, wrong one. Erect a derrick, a larger one, and drill a horizontal well. So you first of all drill the well, and then you install the casing. Casing in this case, well, in most cases, is steel. It's typically 4 to 6 inches in diameter with a wall thickness of around a quarter of an inch. You block the end, and then you position and fire explosive charges to produce radial holes in the casing so that you can access the rock outside from the inside of the casing. On the surface, you mix up your hydraulic fluid, which is mostly water, but a lot of other things besides. And then using diesel generators on the surface, driving pumps, you pump the fluid into the well, and you need something of the order of 2 to 4 million gallons of fluid. Pressurizing is anywhere between 5 and 15,000 pounds per square inch. So 10,000 pounds per square inch is about 600 atmospheres. You need to sustain it typically for some time between 3 and 10 days, depending on the rock. And then when you think you've done the fracturing you need to do, you let the frac fluid exit. I'll tell you a little bit later about what's in the fracturing fluid. One of the key components of frac fluid are what are called proppants. These are small particles of silica, typically high-quality sand, which are used to effectively prop open the cracks that have been made, or in most cases remade, by the fluid pressure. So that when you pump out or allow the frac fluid to exit, the sand, the proppant, stays behind to prop open the fractures. So in this so-called flowback time, what's coming out of the well is a combination of fracturing fluid and the thing you're trying to get, namely the methane. So you have a combination of fluid, liquid fluid, and gas coming out. I should mention that a significant fraction of the fluid that you put in to pressurize the formation is actually lost. It goes somewhere underground and you never get it back. Because this is not inexpensive, companies try, in fact, to preserve the frac fluid so they can use it again. But typically, they might lose up to 60% of it, and so they have 40% left. So you try to store somewhere the residual frac fluid for the next cycle. So fluid pressures, like I mentioned, cracks are typically less than 5 millimeters, but actually typically smaller than that. Cracks extend larger in the horizontal direction than in the vertical direction because of the pressure difference. And you need to sustain it from like 3 to 10 days. And you might repeat the fracking process in the fracking cycles, maybe 5 to 15 times. On the diagram I'm showing only 4 such fracking cycles. A little bit more about the process. The first thing you have to do when you think you might find a place where there might be oil, there might be shale, is to do your seismic exploration. And when you think you've done, this is using typically what you might call acoustic radar is one of the main techniques, but there are other techniques. And this is really quite sophisticated in terms of the accuracy and the information which can be generated from on the surface. But in terms of trying to determine quite what's the methane content of the shale, that pretty well needs to have some kind of vertical drilling in order to show up what you're looking for. You need to take samples. This is an example of an acoustic image of an underground shale formation from, I forget which company. Okay, when you've decided that this is economically and operationally worthwhile, then you need to do what's called, you have to construct what's called a pad. The pad is your location where your future extraction process will take place. It's where you bring all your hardware. So this is a picture of 2 typical pads in the Marcellus play is a word used to describe the zone, the operation in which the extraction will take place. It's on the surface. Marcellus is half in Pennsylvania and half in New York in the United States. So you bring all your hardware, the power generators, because you're not going to have a big electrical cable, so you have to generate your power on site, and compressors and lots of other hardware which is needed. You also need to assemble all the inventory you need for the fracking process. This is some of the kinds of things you need in the frac fluid. That all has to be assembled. Then you begin your directional drilling, a big derrick like I mentioned earlier, to drill. When you're ready to fracture, you put in a thing called this gun, this perforation gun. This is a piece of hardware where you lower to the end of the casing where you want the fracking to take place, fire explosive charges, and produce radial holes in the casing, and you can see some of the holes here. Here's a picture of, I'll show you some bigger pictures a bit later. All I'm trying to show here, this is a quite seriously industrialized zone. It's typically about the size of a couple of football fields, depending on how many wells the operators intend to drill. Another picture. So the composition of the fracking fluid, obviously a lot of water of the order, well, we'll tell you how much in a minute. The proppants I've already mentioned. It's typical, required to clean out the casing to get rid of all the cement and mud that's in the well, and to clean up the rock fractures, one uses typically hydrochloric acid. And then you'd also like to get rid of bacteria because they cause damage. They produce hydrogen sulfide, which damages some of the gelling agents which are used down here. I won't go all through these in detail, but a whole series of different, sometimes apparently conflicting functions which are needed and for which chemicals are used. So how much? Water, typically 2 to 10 million gallons. Because we're talking about steel casing, this cannot be anything other than pure. It can't be salt water, so it's pure water, it's fresh water. A few hundred tons of sand per frac job. And then the chemical additions, typically it's only 0.5% to 2% of the total fluid. But since you've got a lot of fluid, this works up as quite a number of gallons of, typically it's up to 100,000 gallons per frac per well. All this stuff has to be delivered to the site. And here's some pictures of this is a Halliburton operation. In the back end is a formation in the United States. And this is the storage of the water that's needed, quite a lot of water. You have to mix all this stuff ahead of time. And this is the hydrofracturing in progress. Okay, so that's the process. Okay, is that the end? Unfortunately, that's not the end, because of a certain important feature, again, relating to permeability, and that is the rapid decline in the production rate of the wells. This picture shows a plot of the production rate in millions of cubic feet per day as a function of the year. And so you can see that this is the production rate at t equals 0 in the first day, the first week, the first month. But by the end of the first year, it's dropped to about 30% of its original thing. And after 10 years, it's very small indeed. And the other curve is the integrated, the cumulative take from that particular well. So what do you do about this problem? That's the problem. Rapid decline in the production rate gives you a serious cash flow issue, a serious cash production issue. So the solution is to drill more wells in the shale formation. Here's another way of saying the same thing. This is very recent data from 2012, I think it is, where somebody has looked at shale gas plays across the whole of the United States and taken the fact that basically only about 7% of all the oil and 1 or 2% of the gas and 1 or 2% of the tight oil is taken from each play. So if a survey shows that there's squillions of cubic feet of gas in a shale formation, you shouldn't imagine that this is all available, because typically you're only recovering less than 10% of this. And the rate at which it comes out declines by up to 90%, between 65 and 90% in the first year or so. So again, it's the geology which is causing the problem. So we solve this problem by drilling more wells. So how is this done? Obviously, if you invest a huge amount of money in assembling a lot of hardware on your pad, it will be very helpful if you need now to drill more wells, if you could share some of this stuff out among the different pieces of hardware, among the different wells. So here's a schematic of a pad on which here's the pad, and there are 6 wells. You have to imagine this is going vertically downwards and then off in this direction, vertically downwards and then in this direction. And so you have 6 tightly coupled drilling formations in order to effectively not miss out on any of the shale. So this schematic shows 6 wells. This is one from a picture from Chesapeake, which shows 4 pads assembled. Here's 1, 2, 3, and there's one under here. So they're a mile apart in this direction and 2 miles apart in this direction. And so you have, I guess it's 24 wells. Is that right? Yeah, 24 wells. And they're positioned, each of the pads is like a mile apart in this direction and 2 miles in this direction. And taking that to its next level, since you don't want to miss out on anything, this grid is overlaid on a map. And it's going off in this direction because the seismic surveys have shown, in this case, that the predominant direction of the natural fractures is in this direction. So they're going to drill in this direction so that they intersect the maximum number of fractures, because that's the source of the gas. You have to get to the fractures. The red dots show a pad. So basically there's a pad on every one of these different sections. And to see that in real life, this is a pad development in northeastern Pennsylvania, described as a medium scale development, and each of the white dots is a operating pad. So you can see this is distributed but dense. But this shows you the distributed nature of the activity. This is Bradford County, which is a highly fracked region in Pennsylvania. Each of the different colors, and shows the activity of a different company. The plan is to drill, well, the plan was, whether it is the same now, it's not clear, to drill 100,000 wells in this county. So this shows the situation in the US. The early work was done in Texas, in the Barnett Shale, and in Eagle Ford, and more recently in Pennsylvania. This is the biggest formation. This formation here is a very big shale formation, half in Pennsylvania and half in New York State. And you can see, if you want to, the size of the United Kingdom by comparison. Okay, so are there any consequences of this that we should worry about? Well, there's the best compendium of analysis of this that I've seen is in a report published in December 2014 by the New York State Department of Health, their so-called Public Health Review. The authorities in New York State, the governor, I guess, Cuomo, had 4 or 5 years earlier declared a moratorium on all fracking with a view to making an investigation to see are the suggested detrimental effects, are they real? Do we have evidence? So they spent 3 years trying to produce the evidence, and this is the outcome. Wrong one. Their conclusions. So their conclusions are in a number of areas. Issues to do with air impacts, climate change impacts, drinking water impacts, soil and water contamination, surface water contamination. And in each case, what was determined was that there's sufficient reason to be concerned that applying the precautionary principle, New York State decided that from then on, fracking is the moratorium will continue indefinitely. And that's the current situation it's written here, in New York. So what they're saying is, until the science provides sufficient information to determine the level of risk to public health from high volume hydraulic fracturing and whether the risks can be adequately managed, they should not proceed in New York State. This was December 2014. Since 2014, we've got even more documents coming out, and the analysis that's been done of those show that the majority of them are showing clear evidence of detrimental problems. I don't have time to go through all this, obviously, but I can tell you where you can go look for it if you want to. Oh, this is the source of this material, PSE, Physicians, Scientists and Engineers for Healthy Energy. It's an organization based in the United States. Okay, I'd like to talk about 2 particular issues and talk about some detail on 2 issues. The first one is the issue of well integrity. Do wells leak? Well, the first thing is that when you go look for the evidence, you find that actually the word leak is never used. There are a whole string of different words which are used, all of which mean slightly different things, slightly different types of leaks. So there are 6 different phrases used, all which mean effectively leaks. So these are leaks into the atmosphere, leaks into the aquifers, leaks into groundwater, and leaks into underground faults and fracture systems. So I won't show this. This is a video which shows this is a wellhead and which has been and there's some kind of a flood and which happens to be surrounded by water, and you can see it bubbling a bit like a hot tub, I suppose. There's some data. This is data from 2003. What I want to say is it seems from the data that the issue of well leakage, of integrity of wells, is not a fixed problem. It's been a problem for 100 years, and it seems to be still a problem, judging by the data. So this is data from offshore, which comes from 2003. What it basically shows is this is the percent of wells which are affected by sustained casing pressure, which leak over a period of time. So in the first year, 5% fail. By year 10, we have something like 30% of them failing. And by maturity, if you like, several tens of years, most of them fail. This is data now from onshore, which is produced by a Canadian group. And they looked at several 100,000 wells. And they found essentially the same thing. There's a high number of wells which leak. And in particular, they discovered that there is a significant difference between the leakage rate for what are called deviated wells. A deviated wells is one where the direction changes, so that this is wells which go vertically and then horizontally. So you can see the pink lines are ridiculously high. We have a very high percentage of these wells leaking. This is from a webinar from 2013, an industry webinar. 35% of 1.8 million wells have sustained casing pressure or leak. Now, the issue of well leakage, even if it's relatively small, and it isn't, is a big issue because there are so many wells that need to be drilled. The intrinsic feature of fracking is you have to drill many, many wells. If you have to drill many wells, and you have apparently not exactly, but some more or less constant fraction of them which leak, then you have a serious problem. To try to take this to more detail, the group at Cornell University a year or so ago completed a study where they looked at the compliance records, regulation and compliance records from the state of Pennsylvania. They looked at 75,000 inspection and violation records over this period. And then they looked for data from this whole set of records on integrity issues, and then applied statistics. The paper came out a couple of years ago. Basically, they're showing the same kind of thing, the same kind of percentage of well impairment. This is the one that's very interesting, is in these counties are highly fracked counties in Pennsylvania, and so what they did was to compare the performance or the leakage in wells in the northeast with the northwest. And you can see those which just happen to have a lot of fracking have much higher leakages. So you might wonder, how do wells leak? Especially since engineers go to considerable lengths to try to prevent leakage. This is a typical cartoon or a picture, a schematic of a typical structure. This is the basic casing, this 4 to 6 inch diameter steel casing, but that isn't all that's used. This is at the surface. There's a series of parallel or concentric steel tubes which go down past critical points in the subterranean. So if there are aquifers, they'll try to take these as far down as possible. And this has become, I wouldn't say standard, but very commonly used. Between each of the concentric steel tubes is a gasket material. The gasket material used is liquid cement. So they pump liquid cement in, and then this solidifies. The problem is that liquid cement under these conditions isn't a very effective, it's not a very reliable gasket material. That's one problem, so their cracking occurs anyway. But the other problem is at some point there has to be a seal between the outside conductor, the outside casing, whether it's the production casing or whichever one of these it is, and the rock face. And the rock face, as you go vertically, changes. It's not the same everywhere, so you'll have different issues occurring. Okay, so that's one of the reasons why it occurs. It's a chronic problem which has not been solved as far as one can see. I think I've just about run out of time. Am I due to finish it? I have about 5 minutes left.
Okay, yeah, it's fine, I think.
Is that okay?
Yeah, it's fine.
Okay, so I wanted to say something about fracking and climate change. First of all, some elements of this, maybe you don't need me to tell you this, but The sun shines broadband onto the Earth, including some UV visible and so on. The Earth warms up. It re-radiates, but it doesn't only re-radiate in the infrared. The infrared gets absorbed in greenhouse gases and effectively contributes to warming up the Earth. Greenhouse gases, CO2 and other gases, and in this few slides I want to concentrate on methane. So methane has a high greenhouse gas impact, so we need to get the normal way of describing that, GWP. Global warming potential, sorry, I forgot what it was called. So we need to, the question is, can methane be described as a clean fossil fuel? There's been an argument which says that since we do need to do something about climate change, but not quite yet, and we should use methane because when you burn methane, you produce about half as much CO2 as you do when you burn coal. And when you burn oil, it's somewhere in between. So it looks like it's clean relatively compared to coal. But that ignores an important feature. So I'll click on from this. This is methane. That's the previous one was CO2. You can see what's happened in terms of methane. This is percent of parts per billion of methane by year. And you can see there's a huge increase since 1900. And this is now increasing at an even faster rate after 2010. Intense shale gas production, climate change issues. That's looking at shale gas. Well, first of all, when you burn it, it does produce less coal, that's important. But in production, it's leaked, either intentionally vented or it's leaked. So during the drilling operations, during completion, that means once you've done the fracking and you have a pipe full of frac fluid mixed with methane, and then you have to get rid of the frac fluid so that you can access the methane, you have somehow to separate the gas from the fluid. There are technologies available for doing this, so-called completion, but they're often not used, and so when you take out the frac fluid, the gas is just vented. There are leaking wells during unloading, processing, and transmitting, the whole range of times when methane gets leaked. Methane also produces black carbon during flaring. I'll show you a picture of that in a minute. So this is an issue. We do need to ask about two questions. How much methane is being emitted during shale gas operations, and to what extent is that important? And is methane a significant greenhouse gas issue? So first of all, let's answer the second question. Compared to CO2 as a greenhouse gas, methane is 34 times more potent. Its GWP, global warming potential, is 34 times higher. If you do the evaluation over 100 years, it's 86 times, even more, if you do the evaluation over 20 years. In other words, methane effectively drops out of the atmosphere faster than CO2. So 20 years is a key period to do, but 20 years takes us from now till 2036. So I would say this next 20 years is the most important time from the climate greenhouse gas point of view. Since there was no data available, all that were available were estimates, and the estimates of leakage come from the companies because every fracking operation has to report assessments of leakage through the regulators and eventually to the Environmental Protection Agency in the United States. So there are estimates available. So 4 or 5 years ago, some people, Howarth et al., did an evaluation of all this data, and their conclusion from the data was that if you take account of the greenhouse gas footprint directly of methane, rather than via burning it and looking at the CO2, that shale gas contribution to greenhouse gassing, greenhouse gas to the greenhouse effect, exceeds that of coal. In other words, shale gas, far from being some kind of bridge to some kind of sustainable future, is actually worse than coal when you take account of this assessment of the amount of leakage. So is that amount of leakage real? Or some pictures, first of all, of well, let me get onto that. I don't have time to look at the pictures. The estimates of leakage which the EPA had was like 1.5% of production. These people's evaluation was that it's somewhere in this region, depending on which assumptions you make. These are the first set of measurements I could find. There have been quite a few since. And what's now become clear is that there is significant leakage, certainly considerably larger than this, and probably more than 3.5%. There's some cases where it happens. This is in pipelines. This has nothing to do with the fracking process. This applies to any kind of methane. So this is in Boston. Some people, scientists drove a truck around the streets of Boston and measured methane. The natural background, 1.9 parts per million. You can see lots of places where it's higher. Everywhere where it's yellow, it's exceeded. Similar situation in New York, similar situation in Washington. So lots of methane. I've seen this myself off the coast of the Wirral. There's a gas platform out in the sea doing flaring and also doing venting, and lots of black carbon goes up. Okay, so why is that important? Well, we have a problem facing us to do with the temperature rise of the Earth. This is temperature rise against time. This is actual data. This is called zero only because to normalize things, it's become commonly used to take the average temperature between 1890 and 1910 and call that zero. So these are the measurements going up to about 2005, 2010, and these are projections that have been made. The more recent data takes this a bit further. These are projections based on models which try to model this data and then extrapolate under different conditions. Well, the first condition is that we do nothing, and that's this line here. That's the reference line. This line here is the 1.5 degree increase and the 2 degree increase. These are the so-called warning zones and danger zones. The recent agreement in Paris, people agreed they would try to keep it under 2. Some people said it should still be 1.5. So what do? Well, if we take all the measures that people had suggested for CO2 reduction, we gain a bit. We don't go into no change in going into the yellow zone, into the last warning zone, but we gain about 5 years going into the red zone, if you like. The next thing is to reduce the use of methane and black carbon. That takes us to here. Let's go to the end zone. We take CO2 measures, methane measures, and black carbon measures. It makes a huge effect. And what makes the biggest effect is methane. The methane effect is much bigger than the CO2 effect in the next 20 years. But this is actually what the US primary energy consumption, this is their projection. Rather than reducing natural gas, they're planning to increase it by another 30%. This is my final statement. We're the first generation. This is Mary Robinson in New York last year. We're the last generation to fully understand the seriousness of climate change, but we're the last generation with any chance of doing anything about it. Take-home messages: shale gas extraction is both industrially intense and widely distributed across a region. It has a heavy impact both during and after site development, producing these kinds of pollution. Oil and gas wells do leak with significant problems, and we do have to worry about the greenhouse gas effects of methane. Thanks for your attention.
Thank you very much for interesting talk and presentation. Do you have any question to Professor Dennis? Yeah.
The first question is regarding how efficient shale gas fracking is a conventional gas production in terms of quality and quantity.
Oh, sorry, could you repeat the question? I didn't catch that.
How efficient
Yeah.
is of shale gas fracking in comparison with the conventional gas production in terms of quality and quantity?
Oh, how efficient? I think
That's the first question. I have another question.
well, if we measure efficiency by how much of the gas you get or how much of the oil you get. Conventional extraction is very efficient. I guess the only number I can give you is the inefficiency of shale gas. Typically less than 10% of the shale available you get. The rest you just don't get.
Right.
Because it's locked up in the shale. You can't frack the whole shale formation.
Right. The second question is, how correct the argument of New York State Department, Health Department, in terms of environmental pollution? Here in the UK, we've seen in a couple last years, the many protests went out because of concern of environmental pollution for the groundwater and methane leak. How correct the argument of...
Are you contrasting what New York decided to do with what UK is doing?
Yes.
Is that what you're saying?
In terms of pollution for groundwater
Well,
and methane leak.
Well, I think there's some differences.
Thank you.
Groundwater situation in the US is very different from here. Many places in many houses in New York State have their own groundwater. We typically are taking groundwater. We're taking water from a central distribution. Basically, the local authority or the local water company provides it. So it's a bigger problem in the United States. But actually, the physics of the situation isn't any different. So why would you expect it to be different unless the shale is different? So how do you compare the shale? It's different all over the place, but there are some significant general differences between shale in the UK and shale in the United States, where there's mounting evidence. The shale in the United States typically is broadly distributed. If you look down on it, it's big area, okay? But relatively thin, a kilometer or so. In the UK, it's much narrower formations, but they're much, much deeper. That's the first point. The second point is much more important. The formations in the UK, it's known, are much more heavily faulted. There are many more faults, structural discontinuities. So that's something we have to be concerned about if you're putting in 15,000 pounds per square inch pressures. That's 900 atmospheres. Well, it's not all 900, but typically it goes from 300 to 900 atmospheres is the sort of pressures, as far as I can tell from reading the stuff. So I think that what started me thinking about this was the contrast between one side saying it's hell and the other side saying it's nirvana. And there has to be some evidence somewhere. What I would say is that my own view is that we are not yet at any state where you can say that regulation will make any difference. Because as a person famously once said, the Ten Commandments is a good set of regulations, but it does not drive necessarily what happens. So you can make all the regulations you want, but regulations alone are not going to stop wells leaking if you don't know how to do it. So I think precautionary principle is the key thing here, and that's what I don't hear in the media, from the companies, or from the government. Okay, is that?
Any more questions? Yes, Paul.
How much backing do you think there is in West Westminster for fracking in the Northwest? We understand local government, they want to see fracking in the Northwest.
They want to?
See fracking in the Northwest.
What do you mean by local government? Well, I think that's different from how it is across the Mersey. On the other side of the Mersey, Wirral Borough Council has effectively said it's banned. They don't have any power to do that, and they recognise that. In the same way that the Lancashire, in the file, they've basically had several years of investigation, cost a fortune, and they decided, no, we decide we're not going to do it. They refused to accept the license request. And so now it's gone out to an appeal, and they've been told that this will be decided by Greg Clark, who's the Minister for Communities, I think. So he's going to decide, and it's called democracy. So is there an appetite for it? I think the appetite is based on, from some of the trade unions seem to be very keen on it. from the point of view of job creation. If you look at it, you find that the jobs that are created, many of them, okay, there are jobs, but not huge numbers of jobs, and many of the jobs are experts parachuted in. I mean, you don't recruit somebody who never did it before, you know, to drill a deviated well or to control fracking operation. That's not how you do it. You parachute in people. As it happens, because so many companies are not operating anymore in the United States, there are huge numbers of drilling rigs not being used and huge numbers of expert people not operating. The driver in this country, it seems to me, are the gas companies, who I didn't talk about. The economics of this is very interesting. No time to talk about that. But you know, some of the gas companies who see themselves benefiting. INEOS is a key driver here, and other companies that have a lot of land which they think might be relevant. One company in particular owns a lot of land around the Mersey. Okay?
Any more questions?
Is there any idea about the cost of protection compared
The cost of?
protection per cubic meter for the unconventional
Sorry, I didn't catch the word. Convention?
cost?
Protection.
Yeah.
Oh, production. So what about production, sorry?
Is there idea about the cost when you...
Oh, the cost of production.
Yeah.
Oh, okay, well, I can only give you some round numbers. In the US, it costs like, well, now it's a lot cheaper because there's a lot less demand, but when it was at its peak, it's like getting on for $10 million per well. That's to drill the well. That doesn't include all the junk you need to bring along as well. In this country, basically the cost of doing it relates to what is the prevailing demand for the hardware and the people. So at the time when shale gas was driving crazily, as it was like 3 or 4 years ago, because many of the shale companies have shut down in the last couple of years in the United States. And those that were driving shale gas or extracting shale gas in Pennsylvania, some of them, 3 or 4 of them, have moved to Ohio to a particular different shale operation where they're taking oil out of the ground because the price of oil is higher than the price of gas, relatively speaking. So the economics of this, some people have described it as a Ponzi scheme, because pretty well all the companies that are involved in it are small. They don't have great resources. They only have investors. And keeping the investors happy, keeping them paying is a real big problem. So it's only when you have bigger companies coming in, like INEOS. INEOS have a major chemical operation in a number of parts of the UK, notably in Grangemouth near Edinburgh. And so they have a big need for feedstock. Right now, they're either doing or planning to get liquefied natural gas supplied from the United States. But that company has taken a number of the licenses in the Bowland Shale, between here and Sheffield, for example. I didn't mention this. The shale formations go south from Chester down through the border country and into the Midlands. I can't give you a number for the production rate, but it's, personally speaking, aside from any other issues of environmental concerns, I wouldn't invest in it as an investor, that's for sure. I think it's extremely risky. Well, I think it's, one of the reasons it's risky is that whenever people find out what the facts are, they tend to be a little concerned about it happening next door to them, because there are some incredibly cowboy operations. I mentioned the frac fluid comes back up from you have to take the frac fluid out of the casing so you can get the gas out. Some people show nice pictures where this is being stored in steel containers. What actually happens is that the frac fluid is stored in open pits, adjacent, basically on the pad. So 3 or 4 times the size of an Olympic swimming pool, filled with not only the junk you put down, but all the naturally occurring radioactive materials and all the other hydrocarbons which come from this, which come back up in the fluid. They're parked in this thing. In the US, such pads, including these frac fluid ponds, can be as little as 50 meters, 100 meters from people's houses. And of course, the frac fluid is a problem. They have to get rid of it somehow when they finish fracking in a particular place. So one of the ways they have been trying to do this is to reduce the volume, is they put fountains in the ponds. And they fire the stuff up into the air to accelerate the evaporation process, which is, of course, wonderful for the local people who are powerless to do anything about it, it appears. So all those relate to production cost in a roundabout way.
Maybe the last question.
Hi, very interesting. Lots of stuff in there I didn't know before. Lots of the counter narrative to what you present today you hear on the television, obviously. Now, what worries me is the things that you've brought to my attention today. I didn't actually know. So, is there an opportunity? Is that stuff going to be filtered into the public domain more widely? Because when you hear it on the television, all you hear is how wonderful things are. Small amount of chemicals, lots of gas, lots of drugs.
Well, I think that there is, I don't want to get sued, but there is a strong tendency in what is said by gas companies and politicians to have a grain of truth. They'll say, fracking, we've been doing it for 50 years, no problem. Well, it's true. If you frack the way fracking was done in the 40s, it isn't a big problem. But when you factor in all the other issues, the fact that the fracking is one small part of the process, and that you need a whole load of other technologies to make it work, and it's not as though you can get around the fact. The permeability of shale is the permeability of shale, and you're not going to change it. So at the very least, you have to drill loads and loads of wells. I mean, thousands of wells. They're talking about 10,000 wells on the Wirral. Now, nobody said, I'm going to drill 10,000 wells on the Wirral. You just look at what's being proposed, and you think, well, they can't possibly make money if they drill only one well. Or 2 wells. That can't be done. So nobody's going to do it they're not going to pour money down the hole. So you raise the issue about why don't we know about it? Well, for the same reason I didn't know about it before. How would I? And if people tell you something, you tend to believe them. But until you know otherwise. I think that politicians have something to be held to account for here, because I think if somebody tells you something and you believe it, then you become an advocate. I think that it suggests that you or somebody in your team could easily have done, half a day's digging to find out, is there something behind what all these people are complaining about? And, there is real scientific evidence, about water contamination, about air pollution, about leakage. And it's not difficult to find. Once you know you're looking for it. So I can't answer the question because I don't know many politicians. The only politician I know is the MP for Wirral West, who was just being elected in last year. And she ran on a anti-fracking, anti-underground coal gasification, only conventional extraction technology. And I think the result was a big surprise. She unseated a sitting cabinet minister. So how do I know whether that had any effect? But I choose to believe, I hope it did. So I don't know what other politicians think. I'm surprised that so few of them seem to want to pick it up. I'm also surprised that our wonderful investigative journalism we seem so proud of doesn't seem to, well, it doesn't provide the public with what it needs to know. Because I contend that this stuff is not difficult to understand. There's a sequence you can see of where it leads. And, you know, the physical properties, you make a big deal out of it and call it science, but it's pretty obvious once you've understood it a little bit. It's not a big deal. No big differential equations, and I haven't made any. It's not difficult. We should know about it. I said I wasn't going to try and persuade you of anything. I always start off with that as a thing. I have tried to show on each of the slides where there's numbers, where the numbers came from. So you can check it if you want.
Thank you very much.
Okay.
So we can continue now our postgraduate presentation. The next presenter will be Wal El-Harbi. Okay, you have 10 minutes for talk and 5 minutes question and answer session.
Okay, that's
So
fine.
this is Wal El-Harbi. He is going to talk about development of machining strategies for vibration machining.
Good morning, everybody. Welcome to my presentation. It's about development of machining strategy for vibration machining, or in our case, milling. We're going to introduce milling and grinding machine, project aims and objectives, novelty, control system, some simulation results, calibration results as well for displacement, experimental setup, experimental result, conclusion and further work. Milling machine or milling is a machining process which the ship can be removed from the workpieces as it feed against the rotating cutter. Milling operators can be classified into two types, peripheral milling and face milling. In peripheral milling, the cutter coming horizontally on the workpieces. However, in the face milling, coming horizontally. Vertical, sorry. This is grinding machine. Grinding machine, it's operation in which material is removed from the workpieces by powering the wheel. We got 5 types of grinding: surface grinding, and cylindrical, centerless grinding, and then the internal grinding. This project aim of to design and model, build and control a 2D piezo actuators for the milling machine, aiming to converting shutter button into the functional surface, as we're gonna see later. The novelty, we're gonna improve the finish surface quality, button definition on the finish surface, oscillation induced shape breaking effect, so we're gonna have less friction. Improve cutting efficiency with the low cutting force. Oscillation may reduce the load per tooth, so can reduce tool wear. Oscillation may keep the cutting tip sharp, so we're gonna get increase tool life. This is the example of the shutter in the workpieces, as you see it here. This shutter usually coming when the milling machine or the the milling machine and function of the milling machine. For example, spindle speed reach the produce the frequency which is meet the national frequency of the milling machine. In that case, you're gonna produce the shutter. We're gonna study this shutter frequency to develop machining strategies to contract or to convert this button into functional surface. Control system can be classified in two types, open loop and closed loop. In open loop, we're gonna obtain a desired response without any knowledge about the output. So we don't care about the output. However, in closed loop, we use a feedback signal to compare the actual output to desired output response. So in this case, it will be more accurate than before. This is the design process of control system. We're starting with establish the control goals. Second, identify the variable to be controlled. Then write a specification for the variable. Next, establish this system configuration for identify the actuator. Obtain a model of the process, the actuator and the sensor. Next, describe a controller and select the key parameters. Next, we're gonna optimize this parameter using several methods. In our case, we're gonna use genetic algorithm and analyze their performance. If this parameter meet our specification, we're gonna finalize the system. If not, we're gonna repeat step 4. This is the milling machine. Which we're gonna to use in our experiment. It can take power up to 2 kilowatts and the torque 130 Newton meter and spindle speed up to 12,000 RPM. And the table can be movement. The table can be movement in 3 axes up to half a meter, as you see here. This is the sensor dynamometer, which can measure 3 forces, X and Y and Z, as well as the torque. This device can measure feed force and slide force and torque in drilling and tapping as well. Measuring during the cutting force in milling and grinding. Testing of torque wrenches. Measurement of starting torque and for of small motors and step motors. This is the experimental configuration of dynamometer set test, and you can see the power supply to supply the charger amplifier of the acquisition system. This is our forces sensor dynamometer. and this allow few code to record data. This is the result of the calibration. We have calibrate in 3 axes, in Y, in X and Y and Z. This calibration, the benefit of this calibration to find the relationship between the output of dynamometer, which is in millivolt, and forces in Newton, which was in our case is weight in Newton. For example, if we take this graph, when the output of the dynamometer coming in up 55 millivolt is equal 10 Newton. So when we're gonna get the 55 millivolt, so we can know the forces in that case is it's 10 Newton. This is the displacement calibration for our system, and we fit eddy current sensor to get the movement displacement of our system, oscillation system. We have applied the sine wave signal to this oscillation system, and we define that our system is smoothly move as a sine wave, as you see from this graph. And this table is the full range of calibration against voltage and frequency. As you can see here from table, we got the maximum displacement at 150 hertz with the 8 voltage. This is all, this graph shows the full calibration result. In general, by increasing the input voltage with the specific frequency, the displacement will be increased. In our case, we choose 4 voltage and 100 hertz as optimum displacement, which range of 125 micrometer. This This experimental configuration of our system before we start the experiment. This is the some experiment result talking from dynamometer, which measure force. This figure shows the constant force correspond to the steady state forces condition with the tool leave the workpieces. So from this one you can define the time of grinding and forces as well. These 2 graphs show us the comparison between the vibration and non-vibration system. For example, in the normal force with the vibration, we can reduce the forces up to 50%, and in tangential force we can reduce up 60 or 65%, as you see in here. This is the real data we collected to identify the system. This is the input data in the green, blue, and the red is the red is input and blue is output. You see there is a delay between them. We have done a method called the parameter space method to identify the system, and using the process method we define this transfer function, process transfer function of the system. And this transfer function, when we simulate it with the outputs, is got fitting percent up to 83% of fitting in measured or actual measured data, output data. This is the table of to define the parameters of BID controller. In our case, we use this equation, three equations to define the parameters of BID controller. We can define it from transfer function we've mentioned before. Then we find these parameters, and we apply it to BID controller equation. Then we test the performance of this BID controller, and we define the rise time is 0.1 second or 2 seconds, and the overshoot is up to 7%. This one is quite small, and settling time is 0.04 second. This is the 2D oscillation system been designed by our team. We're gonna produce the circle movement, oscillation movement. For the conclusion, the LabVIEW code was developed for data acquisition and measurement. The displacement of 1D oscillation system has been calibrated using AD current sensor. The 4 component dynamometers have been set up and tested for the forces measurement. Experimental result including the forces based open loop and open loop system is oscillated together with the result. BID control parameters and their performance has been defined. An initial design oscillation system with the 2 axes has been developed. For further work, we're going to optimize the performance of BID controller using several methods. Full milling test with a fully controlled signal, a single axis oscillation of the workpieces in conditioning of dry and coolant. Further analysis of obtained data for the 2D oscillation system, manufacture the 2D oscillation system. At the end, we're gonna design the two-dimension control for the 2 axes in LabVIEW. Thank you for your attention. And if you have any question, I will be happy to answer.
Okay, thank you very much. Do you have any question for Wal Harbi?
You mentioned genetic algorithms as part of your control system.
Yeah.
How far you didn't go on to elaborate about it at all? Have you done anything with that yet, or is that something you propose to do?
It's just further work, like optimize my performance. It's not real. It's not main part of my project.
So you haven't done it yet?
No.
But you're thinking of doing it later?
Yeah, like optimize things, optimize my control. Thank
Any
you.
more questions? Maybe I have one question to you.
Okay.
You say your name, you want to convert the chatter pattern into the fractional surface.
Yeah.
Have you identified any fractional surface? What kind of fractional surface you want to make it?
There is, it's dependent on the milling machine itself. For example, some paper defined in the 16,000 RPM, 1600 RPM. It's cause chatter in 350 hertz. So we got, in our work, we're gonna test this frequency with specific amplitude to see how can avoid this chatter.
because we are a bit over time. We run over the time because we need to make it up. So I will be limiting the question time so that we can pick up, because we have elevator speech around 12 o'clock when we have the dean to come and look at it. So our speaker here is Tavia. She will be talking about the cells. Can we improve cell migration? Okay, give us the answer.
Okay. Hi guys, I'm Tavia, and I'm basically talking about fibroblast cells, and basically I'm vibrating cells. So simple as that, vibration. And what I'm going to talk about today is some background, rationale, aims, methodology, results, conclusion. Okay, starting off. We all have cells. I'm sure you all know what cells are. And what I'm focusing my research on fibroblast cells. And these cells are very, very important. They play a particular role in wound healing. And so when you injure yourself, these cells actually are there present to make your wounds heal a lot faster. So the cells that I've used in my study are LL24 cells. These are human lung fibroblast cells. So these are actually from a 5-year-old male, and they're proper lung cells. It's not going next. Yep. Right. So basically, what I'm going to talk about now is that what we're interested to know as well, with the fibroblast cells, that they migrate a lot, so they move a lot. Cells actually always move a lot. So it's interesting to know whether whether vibrating cells is making the cells to move a lot faster, because we want the wounds to heal faster, so we want the cells to move faster to heal the wounds quickly. So what I'm going to talk about is cell crawling, and this is showing, it just shows how the cells move to a certain place. So when the cell is ready to move, so just imagine a slug. So when you have the slugs, they move the first part of the body, and then they push the rest of the body. Basically, that's what happens to a cell as well. It's that this part, you get a lot of actin. Actin is a protein, and that protein is used when the cell's ready to move. That protein goes towards the end of the cell, especially towards where the cell's moving to. So say if I'm moving that way, the protein will go here at the front. So then that's where this is this mesh structure. This is called laminopodia, and this is called filopodia. So when the cell's crawling, you get a lot of actin, a lot of protein produced at the way it's facing. So there'll be a lot of actin here, and I'll be pointing towards this way. So all the protein will be pointed towards that way, the way the cell's going to move. And we also have these adhesion points here. And because the cell is stuck on, so when it's ready to move, these adhesion points, they move up, so they lift up, and they move just a tiny bit forward. So it's basically the cell just drags itself forward. So that's what the cell's actually moving. This is called cell crawling. So like I told you, you get a laminopodia, and you get filopodia, and so you get this is the leading edge. So when the cell is ready to move, so you get a lot of actin coming towards right at the end of the cell, and then the cell is ready to push forward. The rationale. Basically, how we've evolved, our cells have evolved as well. And so what they do, the cells actually, they can sense the surroundings. And when they sense the surroundings, they can convert that sort of energy, so say vibrations, so they can sense the vibration, they can convert that vibration into biochemical signals, and this is known as mechanical transduction. And it's an important function for the normal biological functioning. However, because it's a relatively new thing, not very many people know about it. So the literature review I'm going to talk about, basically, these are what sort of studies that I've done before, and people have looked at looking at bone cells, and they vibrated these bone cells, and they've looked at when they vibrated the bone cells, you get more attachment, proliferation. You get some sort of you get these stem cells as well that are growing as well. So you do get a lot of good stuff by vibrating. So what I was interested to know, using that concept, is using fibroblast cells to see whether I can encourage the wound healing process. and to know that like basically diseases such as diabetes, sorry about that, like diseases such as diabetes, their wounds, people that have diabetes, their wounds take ages to heal, and so you want to make their healing a lot faster. So if we can use that concept of vibration, we could actually maybe help these people to get the wound healing to happen a lot faster, so people won't be there like taking ages for the wounds to heal. So there's a lot of lack of knowledge out there because it's a relatively new concept. Oh, sorry. So basically, the aims that I'm actually working on is to see whether mechanical stimulation, i.e. vibration, can actually accelerate fibroblast cell migration. So can we vibrate cells and can they move a lot faster? And then I looked at the cell morphology, again, looked at how the cells moved, so if the cell crawling was encouraged, or was it like, it was just nothing happened. And I'm also going to look at whether, when you vibrate in cells, am I killing the cells? Because I don't want that to happen. So we were looking at that as well. So this is a vibration device that I use as a speaker device. And this is, basically, I'll just go through. This is actually the speaker. And this was actually placed into the incubator of 37 degrees Celsius and 5% carbon dioxide, and it's waterproof because my dishes were put on top of this speaker and they were vibrated inside the incubator. Now I can show you here quickly. This is my speaker device. I'm going to pass it round. This is a simple £25, very cheap to make. So just imagine if you can have little speakers. We can have these little speakers in the lab or in the NHS. We can maybe I'll apply these vibration devices to people. It'll encourage the wound healing process, and it's very cheap. It's £25. The whole control and the whole setup. Basically, the methods that I've done is looked at the cells were grown. The cells are actually my babies. I actually grow my cells, and the cells that grow, they use medium, which is like full of glucose and like fetal bovine serum, so they need a bit of meat. And they use antibiotics as well. And this is a flask that the cells grow on the bottom of the dish. And to use them, when the cells are grown, they attach to the bottom of the cell, at the bottom of the dish, of the flask, sorry. And trypsin, which is an enzyme, is used to make the cells detach from the flask. And these are my little 35 millimeter dishes that I use in the lab. So these is where the cells are grown on the bottom of there, and this is a dish that's placed on top of the speaker in the incubator, and it's vibrated. So this is speaker. It gets the dishes get vibrated, and then I looked at single cell migration. So when the vibration was applied, the dishes were placed onto a microscope, and every 5 minutes an image was taken and a video was made. So this shows a video of the cells that were moving for 4 hours. And then to rule out whether cell viability, an MTT assay was carried out, and then an actin staining. This is like looking at the actin polymerization. So when the cell's crawling, like I said, you get a lot of actin at the end of the cell. So basically, so I did actin staining. So this is a video, which I hope it works. Yeah. Can you see my cells are like moving around? Yeah. So basically, this is a control. This is on a normal day. This video was made over 4 hours. So an image was taken every 5 minutes. So that's how the cells move after 4 hours. And this is using 5 minutes of mechanical stimulation. So these cells were vibrated. So you can see the cells are moving again. Can you see them? But when I measured them, I used ImageJ, a software, and I tracked these cells over the period of 4 hours, and I could tell how much these cells have moved. So the results that was obtained, over 4 hours, you can see I used a frequency of 100, 200, 400, 800 and 1600 hertz, and so you can see that the 100 has shown more cell movement, so more cells were moved, and 1600 it was kind of slowed down compared to the control. This is the MTT assay. Now it shows that basically the cells are viable, like it's in like the cells were not dead. So this is a really good sign, which is a positive for me. And this is, remember I told you about the, you get a lot of actin. So the white stuff, you can see all the white stuff here, and at the end of the cell, this is all actin. And if you can see that you don't get a lot of actin at the end of the cells with control, but when you increase the vibration, so you get a lot of like leading edge, so you get a lot of these cells are ready to move and crawl, so you get a lot of actin polymerized. So basically, what I found out was vibration works, the cells move, 100 hertz works perfectly well, 1600 hertz slows down, so which could be used for people that have cancer and when they go, when they have radiation. So when people have radiation, especially when it's breast cancer, the external cells, they migrate and goes into the liver and can cause secondary cancer. We don't want that to happen, so we can maybe control the migration of 1600 hertz, so maybe apply like a piezo or something around the area so that the cells are controlled, so they get the maximum dose of radiation and the cells, what's it called, get killed there and then. Thank you very much.
One question, please. Only one. Okay, you go.
How did you control the movement of the displacement? I didn't show you my displacement results, so you're one step ahead. But anyway, yeah, the speaker has a displacement values that a Polytech company came and measured the displacement values, and they started off with 9 micrometers of 100 hertz, and it was 1600 hertz. It was 1 micrometer. So the displacement was, but I haven't controlled the displacement for this. So it's something that I'm going to look into next. As the next step, I'm going to repeat all my experiments with the using the speaker with displacement controlled, using a resistor.
Well, one question.
Yes.
Please. We know very well that vibration is harmful for human body.
Yeah.
So if you in this example, you are vibrating the cells.
Yeah.
How you intend to vibrate a human being in order to reduce or improve the cell migration? How will you do that?
Using a small piezo. A piezo will be used, and piezo can be placed on top of the wound. So you can apply like 5 minutes. I looked at 5 minutes and 20-minute vibration. I only concentrated on 5 minutes. I have a lot of data, so I can't add it all in. But a small piezo will be applied onto the wound and vibrated, and it was like maybe 5 minutes, and then you can get more wound healing process.
Thank you.
Okay.
Our next speaker, we have to jump one because we can't make the 15 minutes. But now we're going to jump straight forward to the speaker who's talking about non-destruction evaluation of and live monitoring of solder joints in RF packing. That is Adeni. What is it? Come up. You can project your voice, you don't need a microphone. Okay. Your time, sir.
Yeah. Thank you, Dr. Batako, for the introduction. My name is Adini Olumide Ayodele. I'm here today to talk about my project, which is non-destructive evaluation and life monitoring of modern electroencycleboard. Act 9, please. I'm going to talk about the introduction, the aim and objective, the motivation of the project, the methodology, the discussion, conclusion, and future work. Introduction, please. Electronics are integrated in every aspect of modern device. Nowadays, modern industry are now making use of modern electronic circuit board to design their products so as to make it reliable, durable, flexible, and to exceed customer demand and expectation. Example of industry that are making use of electronic circuit board, we got automotive industry to make different parts of cars. Nowadays we have electric vehicle, telecommunication industry, transportation industry, ministry, etc. But the question is, how long will the components last? Next slide, please. The motivation of the talk. In the design of electronics, flip chip technology has been adopted for high density packaging, owing to the great electrical connection and high heat dissipation. In flip chip assembly, so that joint does not only provide conventional function such as electrical connection or high heat dissipation, but also provide precise alignment between the chips and the package. Therefore, the reliability of solder joint is so meticulous. And number two, to improve traditional approaches in product development. What most people do nowadays is to design. After they design, they build. After they build, they test. After they test, they detect fault. If there's any fault found, they repeat the procedure 3, 4, and 5 until not yet break or they run out of money. And this is cumbersome and it consumes a lot of time and money. Last December, according to BBC, a crack, one of the faults that resulted in the crash of Air Asian 320 was a crack in solder joints in channel A and B, resulted in the loss of electrical connection and led to RT and U failure. This made this project so interesting and so applicable to the real world. Aim and objective of this project, please. The main aim of this project research work is to develop a non-destructive ultrasonic monitoring system aiming to aid testing procedure and ensure high-quality live monitoring of solder joints in area repackaging. Objective are, I'm going to perform validation testing, I'm going to perform non-destructive testing, I'm going to develop image processing and feature extraction. After that, I'm going to perform data fusion to fusion the data from AMI and the X-ray and the 3D X-ray so as to get a better result. Novelty. The better we understand gradation and failure, the better we can make a prognosis on time into mission life when the product will fail. In this project, I'm going to use a new thermal profile to test the reliability of solder joint. After that, I'm going to consider the impact of floor plan layout. What do I mean by floor plan layers? I'm talking about how the components, how the chips are being placed on the test board. After that, I'm going to fill data to be evaluated by X-ray and microsectioning, 3D and 2D acoustic scan to be collected at regular interval. The feature extraction of data in which random image processing resolution will generate to capture the statistical variety of possible features and calculation will be performed. Methodology. Because of my time, I will not be able to elaborate on each step. But the first step is to design a test board. As test board was designed, and on that test board, I've got 14 flip chips. 8 flip chips are BGA, while the other 6 are called the flip chips that I use as a test vehicle to test these 8 BGAs. From under these chips, I've got 109 solder joints under it. I've got 109, 109, 109, 109, 109, 109. You know, it's going to consume a lot of time to scan each of the joints one by one. So I selected the upper joint and the lower joint. I selected this part and this part. I consider them as a good joint because they are symmetry to the symmetry of the chip structure. Why I choose the edge size, because I know that if it's going to develop a fault, it's going to break asymmetry to the symmetry of the chip structure. So far, so good. ATC test was performed at DEFI. This is the flow chart that I used to perform the ATC test. The purpose of the ATC test is to age the lifetime of the board in a short period of time. If, for example, if I designed the board and I said this board is going to last like 5 to 10 years, I can't wait so long no. So I need a test that is going to accelerate the lifetime of that board in a short period of time. As you can see, this is the experimental setup in DEFI. It's also far. I perform one test without no PCB, another test with PCB. The reason why I perform tests without no PCB was that it is paramount that only the environmental condition you are trying to test is the only one present at that particular time, because any other factors like vibration might contribute to the failure of the joint. As you can see, this is the second test with PCB. I use a thermal profile of minus 40 degrees centigrade to 128 degrees centigrade. The dwell time to be 35 minutes, while the wrap time to be 5 degrees per minute. I performed the test for 4 cycles. And this slide diagram just give us details about the experimental result. You could say the test duration, this side is the minimum and maximum temperature, while this side is the dwell time, while this side is just the wrap time. After performing the ATC test, as I said earlier during my methodology, I need to perform non-destructive test by using AMI. What is AMI? AMI is acoustic microimaging. What's the function? What's the purpose of acoustic microimaging? It's a device that uses high frequency to penetrate an object and detect whether there's void, delamination, or defect in that object. Benefits of AMI, as I said earlier, it is not destructive and it could penetrate my test sample material, Working principle of AMI. From this diagram above, it's blurry. From this diagram above, when an ultrasonic wave encounters a boundary, 2 things happen. One will be reflected and one will be transmitted. The one reflected will tell me the condition of the test sample I'm trying to inspect. When I'm talking about reflected wave, I'm talking about Z2 minus Z1, we all these physics, over Z2 plus Z1. When I'm talking about the acoustic impedance, which is the product of material density to the ultrasonic velocity. From this diagram, this is the reflected wave. This first echo tells me the front surface of the material I'm trying to respect, while this one is the one I showed previously. I'm still going to show it now. Tells me the next subsurface echo of the material I'm trying to inspect. So far, so good. I use different type of transducer for this experiment. First of all, I use 50 megahertz to scan AO chips. As you can see, the pixel size is 25 micrometer, the scan size to be 20.5 millimeter, the resolution size to be 424 times 424 in pixel, please. While in time used to scan is 58 seconds. What I also did, as I said earlier, during the methodology, I select some parts. I consider them to be good joints. I consider the other parts to break first. I also scan this edge part, but because of my time, I will not be able to read that stuff. AMI settings and measurement. This is just the preliminary. I set the trigger level to be 2.966, the gain, which is used to amplify the signal, to be 12, the channel gain to be 22, why the gating to be narrow, so that I could get the X, Y, Z elevation of the test sample I'm trying to scan. I also make use of 100 megahertz because the higher the resolution, the higher the frequency, the higher the resolution you are going to get. This is the diagram of AO chips. Right, this is just the edge effect. I was able to zoom one of the solder joints I selected earlier. As you can see, this is the whole scenario of this project. This gray area is the part connecting to the flip chip so as to provide the electrical connection, the mechanical, and to provide its dissipation. While the outer side are considered to be edge effect. But initially, this is what I'm trying to investigate. I'm trying to investigate how the crack, how the crack will propagate. Maybe the crack is going to propagate from this side, which is the edge side, or from this region of interest. That's the main scenario. So I as I said, that the higher the frequency, the higher the resolution. I also make use of 230 megahertz. This is the diagram of AO chips, LG. I was able to zoom one of the flip chips also. I could get 41 pixels because the wider the region of interest, the more accurate the defect measurements will be. This where the work done so far, you could see it's now up to 4 pixels. VIA module was also developed so as to accumulate, to collate AMA scan data. So it's going to help me to go back to my system and to enable me to get my image without rescanning the whole stuff. We could see this is the diagram for 100 megahertz, while this is the diagram from 230 megahertz. Conclusion, please. Factors affecting resolution of acoustic image. We have frequency, we have focal length, we have signal strength. Increasing solar jet reliability can increase a product lifetime and necessitate customer demand and expectation. Future work, I just submitted my idea, so I've got some work to do. AATC test will be carried out again. Non-destructive test will be performed. Signal processing will be performed so as to separate the signal from the machine. Image processing and feature extraction and data fusion, as I said earlier, X-ray, ultrasonic image. And I'm going to investigate the effect of floor plan layers, how the components has been placed on the test board. Thank you for your attention. Any question, please?
We need one or two questions, but there's so many hands, you may be able to talk to him after that. Now, I'm going to choose you in front.
Thank you for your presentation. Actually, I just want to make sure regarding the scan, what type of scan is involved in your research. And the second question, very quick question.
Oh, you have one question.
Okay.
Give a chance to others. You got one question.
Yeah, basically, the type of scan. Sorry, I need to go back. Yeah, it's a mechanical scan, you know. I'm trying to use piezoelectric. The type of transducer I'm trying to use, or the type of sensor, is called piezoelectric transducer. It's going to scan, it's a mechanical scan, yeah. It's going to scan to and flow in a linear motion, you get what I'm saying? So this is a mechanical scan, please. Yeah.
Are you considering to go further up in terms of your frequency range, or is there any sort of limit that you can go to?
Yeah, basically, I'm not going to use more than 230 megahertz because that's the sensor available at this particular moment. Those sensors are quite expensive, you know. I think one cost close to 15 grand. I'm not sure, but for my research so far, you know. Thank you so much.
Ibrahim, you have spoken already. I'm not giving you the chance. Okay. No question. Okay.